Suppose a boat is moving on still water. In a period of time, it's moved a distance, say 1 kilometre from point A to point B. We can represent the boat's velocity in this direction by an arrow. Okay, now suppose there's a current in the water in this direction and that the speed of that current is represented by the length of the arrow. The question I have for you is, if the boat again travels at the same velocity and direction for the same period of time as it did in the first example, where will it be after that period of time? Point at the screen now. If you pointed somewhere around C, then congratulations, you already have an intuition for how vectors work. What you probably did is reason that in the same amount of time the boat travelled from A to B on its own power, the current would have carried it in its direction by this amount, and so, in a sense, the arrows are added together to get the final answer. By the end of this video, you'll understand exactly why this works and of course everything else you need to know to understand vectors. There are many situations in real life where direction is important. Suppose you're walking with a friend in the same direction, but you're walking faster. You know intuitively as time passes that you'll get further and further away from one another. Similarly, if you're walking at the same speed but different directions, you'll also get further away from one another. So in both scenarios, the speed as represented by the length of the vector and the direction are important to the outcome. Vectors have both magnitude, i.e. length, and direction in order to capture this need to have both in mathematical form. Starting from the origin, the point 0, 0, suppose you walk in a straight line until you reach the point 2, 3. You can imagine, if you like, that this point is 2 kilometers east and 3 kilometers north of where you started. Let's call the vector you've travelled along A. Often we use lowercase letters with arrows above them to denote vectors. There are, in general, 3 different ways of representing vectors. We have the algebraic representation using a letter to symbolically represent the vector. We can draw an arrow which helps visualize the vector and do geometry, and the numerical representation which essentially gives us a formula for how to think of the vector by telling us how much to move in the x and y axes. Let's talk a little bit more about the algebraic and numerical representation of vectors. This is how we would define our vector A. It's common to use a vertical list of numbers which represent how far the vector travels in the x and y directions. It's equally valid to think of this as representing the vector going from the origin to the coordinate 2, 3, as we've already seen. But be aware that there's nothing in the definition of a vector which tells us where it starts. Think of vectors as being relative change. That is, what's important is how far we've moved from where we started and in which direction, but we're not usually concerned with where we started. What you'll usually find when you start using vectors is that in many cases the origin of the vector is clearly 0 anyway. Think of velocity or force, which are vector quantities. The lack of force, for example, would just be 0 force. The individual numbers that make up a vector are called components. The first number, the x component, is so called because that's how long the vector is as measured along the x-axis. The second number, the y component, represents the length of the vector along the y-axis. Vectors can have any number of components. The dimension of a vector is the number of components it has. We've seen how we can represent a 2D vector visually on a graph. We can do the same with a 3D vector by letting the 3 components represent x, y, and z, but for higher dimensional vectors, it becomes impossible to make any graphical representation. Two vectors are equal if and only if all of their individual components are equal. So being specific, if we have two vectors, a equals m and n, and b equals p and q, then a is equal to b if and only if m equals p and n equals q. This is true for high dimensions. For example, if a and b were 3D vectors, mno and pqr, then a equals b is true if and only if m equals p, n equals q, and o equals r. We can add vectors together. Imagine you're travelling along the vector a, ending at the point 2, 3, and then you travel along another vector b. The vector b is 4 units in the x direction and goes down by 1 unit in the y direction. You end up at the point 6, 2. Now, since you've travelled along both vectors, it feels logical that you've essentially added a and b together. That is, it would make sense that if a vector c goes straight to the point 6, 2, we should define addition of vectors in such a way that a plus b is equal to c. This is how it works. Let a equal the vector 2, 3 and b equal the vector 4, minus 1. We define the addition of two vectors as adding together the numbers representing the x components and the y components separately. So a plus b gives us a new vector, 2 plus 4 and 3 minus 1, or 6, 2. Notice this gives us the result we wanted. By adding the x component and y components of a and b separately, the effect is as if we moved the base of b to the tip of a, giving a plus b as the vector from the origin to the tip of b. What I hope you're becoming more aware of is that the x and y coordinates can essentially be treated separately when we're doing operations with vectors. We add all the x components together and then all the y components together completely independently. Would a plus b give us the same result as b plus a? Test yourself and I'll leave the answer in the video description. When talking about vectors, we usually call ordinary numbers scalars. This is because multiplying a vector by a number has the effect of scaling the vector by that number. That is, changing its length by the amount you've multiplied it by without changing the direction. Let's have a look at how this works. Given a vector v with components x and y, we multiply v by some scalar c. This results in a new vector where both the x and y components are multiplied by c. Remember, c is just a number, as are x and y in this example. Applying this to the vector we saw previously, where a is equal to 2, 2, multiplying the top and the bottom by a scalar 2, we get a new vector 4, 4. We can see that this is twice as long as a and pointing in the same direction. An important one to remember is multiplying a vector by minus 1. As you can see, in this case, we get a vector of the same length, but in the exact opposite direction. Question 2. Let a be the vector 8, 4, 1 and b the vector 3, 5, 5. What is 2a plus b? You might have noticed that we've talked about the addition of vectors and multiplication of vectors by a scalar, but not subtraction. Technically speaking, subtraction isn't a usual operation of vectors, but we can and often do subtract vectors. We can define subtraction in terms of addition and multiplication. That is, for vectors a and b, a minus b is a plus minus 1 times b, which gives us exactly what we would expect, the x-coordinate of a minus the x-coordinate of b, and so on. Since minus 1 times b is the same length as b, but in the opposite direction, we can see how a minus b is a shorthand for a plus minus 1 times b. A more useful way to think about subtracting vectors comes across when we shift things around a bit. Moving b back to the origin and shifting a minus b to the tip of b shows that the vector a minus b points from the tip of b to the tip of a. You can remember this as going down b and up a, since you effectively subtract b and add a. If you want the vector that goes from the tip of a to the tip of b, that would be b minus a. Okay, but how is this useful? Suppose two cars are travelling with velocities a and b. For someone in car B, it will look like A is moving away from them with a particular velocity c. Notice that c is the vector which points from the tip of B to the tip of A. So, if A is the vector 3, 3 and B is the vector 4, 2, then c is A minus B, which is the vector minus 1, 1. I want to finish off this section looking back at position vectors. It's common when working with coordinates to see vectors written in a slightly different way. Suppose we have 2 points A and B and the origin O. We often see that the vector which represents O to A as the vector OA, the vector from O to B as OB, and the vector from A to B as AB. From what we've learnt about adding vectors, we can see that OA plus AB equals OB, and as before, OB minus OA is equal to AB. Remember to go backwards down OA, the one with the minus sign, and then up OB. Notice too, you could have got the second equation just by rearranging the first one. In our example of multiplying a vector by a scalar, I said that 2a is twice as long as a and points in the same direction, but it would be more accurate to say 2a is parallel to a. In fact, the definition of a pair of vectors a and b being parallel is when a is a scalar c multiplied by b. Notice that it doesn't matter which side of the equation the scalar is on. I could have written 1 over c, which is still a scalar, times a equals b, and this still means the two vectors are parallel. For example, for a equals 3, 1 and b equals 9, 3, then a and b are parallel vectors, since a is equal to 1/3 of b. Or we could have said 3a is equal to b. Question 3. If a is the vector 4, 5, which of the following vectors are parallel to a? Is it a, 2, 3, b, 3, 7, or c, 2, 2.5? We've seen how multiplying a vector by a scalar lambda gives a parallel vector of length lambda times whatever the length of the original vector was. This means that by varying lambda, we can reach anywhere on this line parallel to A. We can also translate this line by adding another vector, b. And so, we have the vector equation of a straight line, r equals lambda a plus b, where a and b are fixed vectors and lambda varies. As lambda changes, the tip of r will move along the line in the direction of a. The r vector you see on screen shows r when lambda equals 1. If lambda was equal to 0, for example, r would be 0 times a plus b, and so it would equal b. Question 4. Find a vector equation for the straight line which goes through the points 0, 1 and 4, 5. I find it's usually easier to find the answer to questions like this if you sketch it out. The length of a vector represents its magnitude. If you were to walk along a vector, its length would be how far you've travelled. We represent the length of a vector with two vertical lines. We can calculate the length of a vector using Pythagoras' theorem. Taking the x and y coordinates, if we translate the y component, we can see that A is the hypotenuse of a right-angled triangle, with adjacent and opposite sides of length x and y. Therefore, by Pythagoras' theorem, the length of A is the square root of x squared plus y squared. For example, if we have a vector representing velocity v, which is 5, 2, let's suppose the units are meters per second, so whatever it is that's moving is travelling 5 meters per second in the x direction and 2 meters per second in the y direction. What is the speed? That is the absolute speed in the direction of v. In physics, velocity is a vector quantity. It has direction, whereas speed is just how fast you're travelling, a scalar quantity. We work out the speed of a velocity vector by calculating its length. In this case, the length of v is the square root of 5 squared plus 2 squared, which is about 5.39. The way we compute the length of a vector doesn't change regardless of the number of dimensions. We add the squares of each of the components together and then take the square root. If we have n numbers, a1, a2 to an, the sum of those numbers, a1 plus a2 plus a3 up to an, can be written as sigma with I equals 1 underneath, signalling where I starts from, and n on top, which says where we stop. And then the a sub I is the thing we're adding up. We read this whole thing as the sum of a sub I from I equals 1 to n. The mathematical formula for the length of the vector uses the summation sign. Let A be an n-dimensional vector a1, a2 all the way to an. The length of A is given by the formula, the square root of the sum from I equals 1 to n of a sub I squared. From what we've learned about the addition of vectors, we know that we can write any two-dimensional vector as the sum of two. One containing the x component and a y component of 0, and another containing the y component and an x component of 0. From what we've learned about the multiplication of vectors and scalars, we can take this apart even further. We know that 4, 0 is the scalar 4 multiplied by the vector 1, 0, and likewise 0, 9 is 9 times 0, 1. These vectors have a length of 1 and point in the x and y directions respectively. Vectors like this are called unit vectors and are usually denoted as I hat and j hat. For example, if A is the vector 2, 3, then in unit vector form this would be 2i hat plus 3j hat. Adding two vectors in unit form is the same as before. For example, if A is 4i hat plus 1j hat and B is 2i hat plus 7j hat, then A plus B is 4 plus 2i hat plus 1 plus 7j hat, or 6i hat plus 8j hat. The same is true for multiplying by a scalar. In 3 dimensions, the vector PQR could be written as pi hat plus qj hat plus rk hat, where I hat, j hat and k hat are the unit vectors in the x, y and z directions. Note these unit vectors would also be 3-dimensional. We've seen how we can add vectors together and multiply a scalar and a vector. But what about multiplying two vectors together? There are two ways of multiplying two vectors together in mathematics. The scalar or dot product multiplies two vectors together to give a scalar, and the vector or cross product multiplies two vectors together to give another vector. Notice that for each of the products we have the probably more formal names, scalar and vector product, named after what you're left with, and the names dot and cross product, which are named after the symbols we use for each of them. I think in general it's more common to hear dot and cross product, but that really depends on preference. If we have two vectors a equals mn and b equals pq, then the dot product a dot b is given by multiplying the two x components together, m and p, and the two y components together, n and q, and then adding them together. With vectors of higher dimensions, the same formula holds. For three-dimensional vectors, for example, we multiply the x, y, and z components and then add them together. And so the general formula using the summation notation for the dot product of a and b, where a is the vector a sub 1 to a sub n, and b is the vector b sub 1 to b sub n, is the sum from I equals 1 to n of a sub I times b sub I. An alternative formula we could use for a dot b is the length of a times the length of b times the cosine of the angle between them. This link between the dot product and the geometry of two vectors can be really useful. For example, we can work out the angle between any two vectors. If we divide both sides by the length of a times the length of b, we get a dot b divided by the length of a times the length of b is equal to cosine theta, the angle between them. And so the angle between two vectors a and b is given by the inverse cosine of a dot b over length of a times length of b. A useful corollary of this is that the dot product of any two perpendicular vectors is 0. This is because the cosine of 90 degrees is 0 and makes for an easy test to check whether any two vectors are perpendicular. And in general, the dot product is a measure of how well aligned the vectors are, being at a maximum when theta is 0, 0 when the vectors are perpendicular, and at a negative minimum when the vectors point in the opposite direction. Another useful thing to remember is that the dot product of any vector with itself is its length squared. We can deduce this using both methods of calculating the dot product. If A is the vector mn, then A dot A is m times m, or m squared, plus n times n, or n squared, which we've seen is already the formula for the length of A squared. Alternatively, we could use the formula length of A times length of A times cosine 0, which, considering that cos 0 is 1, gives us the length of A squared. Question 5. If A is the vector 4, 7 and B is the vector 1, 5, what is A dot B? What is the angle between A and B? One useful aspect of the dot product is that we can project one vector onto another. What does this mean? Well, if we have two vectors A and B, the projection of A onto B is like the length of A in the direction of B. It's if you draw a line from the tip of A which touches B at a right angle, what is the length of the vector in the direction of B until you reach this line? We can use basic trigonometry to tell us the length of this projection. The length of A, which we can see is the hypotenuse of a right-angled triangle, times the cosine of the angle between A and B. Now, in order to get the actual vector representing the projection by the unit vector in the direction of B, we'll call it A proj for the projection of A onto B. Now we can simplify this. We already know how to calculate cosine theta. Since cosine of theta is A dot B over the length of A times the length of B, we can substitute this into the equation for the projection. We can cancel the two lengths of A, and now we've eliminated the angle from the equation. This is A dot B over the length of B, which is also known as the resolved part of A in the direction of B, and is a scalar which represents how much of A points in the direction of B, but we still have this tricky b hat thing. Well, b hat is the unit vector in the direction of B, and so this is just B divided by the length of B. Substituting this into the equation gives the projection of A onto B equals A dot B divided by the length of B squared multiplied by B. As mentioned previously, there are two ways of multiplying vectors together. We've already discussed the dot product, where the dot product of two vectors is a scalar, but I want to finish with a very brief discussion of the vector product. The vector product of two vectors A and B gives rise to another vector we'll call C. The first thing to note is that this vector is always perpendicular to A and B. Second is that the cross product doesn't work with 2D vectors, only those with 3 dimensions. Unlike the dot product, order matters for the cross product. A cross B is not equal to B cross A. In fact, it points in the opposite direction. The direction can be worked out by the so-called right-hand screw rule. Imagine you are looking down on the plane of A and B. If, when calculating A cross B, the smallest angle between them takes you anti-clockwise, then A cross B points out of the page towards you. If the cross product takes you clockwise, then the product points into the page, away from you. Just like with the dot product, the cross product also has a geometric formula. In this case, the magnitude of A cross B is the length of A times the length of B times the sine of the angle between them. A useful way to remember this formula is that it's equal to the area of a parallelogram with sides of lengths A and B. Also note that this is for the magnitude of A cross B. The direction of the vector in this case would be directly into the screen. Finally, for two 3-dimensional vectors, A and B, we do have a formula for directly calculating the cross product of A and B. This doesn't look particularly nice, but for those of you who know some matrix algebra, this can be written as the determinant of some matrix M, which has the first row as I hat, j hat, and k hat, the second row as the components of A, and the third row as the components of B. Don't worry if this doesn't make much sense right now, it was just to make you aware of things you might need to learn further down the line. I hope this has been useful, and as always, thanks for watching. I'll see you next time.